So in how many ways? The answer is 5 ways. Simple situation. Let's look at 2 other simple cases. We do a lot of things with flipping coins because it's an easy process to duplicate, and rolling a dice. So the question is, if we flip a coin, how many possible outcomes are there when you flip a coin? 2, heads or tails. Okay, so the answer is 2. So one answer is heads. You can just write it down. You don't even need to write it down because you've probably flipped a coin many times. Heads, tails. So I count those, and that's 2. So the answer is 2. Now rolling a dice or die. I always get confused which I'm supposed to say. So if I say it wrong, I apologize. So if you roll a dice, how many different possibilities are there? What's that? A dice. Yeah, so there are 6 because there's 6 sides of a dice. Okay. And a dice normally has numbers 1 through 6, but you could have colors. You could, it doesn't have to be numbers, but and I guess theoretically you could have 2 sides that have the same color. So in that sense, that you might not have 6, but let's assume that all different. It's a numbered dice, and you can have 1 through 6. It's 6. So those are just some simple examples of one-part tasks. So now we're going to have a 2-part task. We're going to have a red dice and a green dice, and we're going to roll them, and we're asked the question, how many possible results are there? And I'm going to erase the last part. Results are there. Just in general. So we're not adding the dice together, we're just saying, so you roll the dice, you get 2 1s. That's 1 and 1. Okay? You roll the dice again, you get 3 and 1. That's a result. If you get 1 and 3, it's a different result because you're going to have a different value on the red and the green in the 2 cases. So the question is, how do you figure out the answer? So when you're usually rolling dice or something like that, and it's 2 parts, the easiest way to figure out how many possibilities are is just to list them, and a table is the best way to list the results from a dice kind of question. So we're going to create a table if it's not already there. There is a table, but let me add one. And it's not 6 by 6, it's 7 by 7 because I need to put the headers on here. So what I'll do is I'll write in red down here. So the red dice can have 1, 2, 3, 4, 5, 6, and the green dice can have 1, 2, 3, 4, 5, 6. So those are all the possibilities of the 2 dice. If I throw 1 dice, I have 6 choices. We already talked about that. The question is, if you throw two dice, what are the possible results? And you can kind of tell the answer is going to be 6 times 6, which is 36. But we're going to actually just list them all. So what we'll do is the first digit will be the red value, and the second digit will be the green value. So you can fill it out if you know how this thing is going to go. You can just fill it out any way you want to, but I'm going to do it color coded so that you can see what I'm trying to do. So the row tells me what the value here tells me what the first number is, and the second number will tell me the green value. Started, and then you forget what you're doing and you start writing stupid stuff. And I forgot one. Forgot a row. Okay, so the answer is 36. There are 36 different possibilities for rolling 2 dice, and different colored dice. Now, once you have this filled out, I could erase that one that says if there are not any repeat, if you don't allow repeats. So this kind of gives you all the possibilities. But if they put some kind of restriction on the counting that you're doing, then you can eliminate stuff, and then so you take everything and then you eliminate the ones that don't apply for the particular condition. So to answer the first question, if we roll a red dice and a green dice, how many possible results are there? Question mark. The answer is 36. And how did I do that? By going over here and just counting how many possibilities I had. I've listed all the possibilities. But I may, what if I say, with the additional limitation where repeated digits are not allowed. So what does that mean? It means 1, 1, 2, 2, 3, 3, 4, 4. Why? Because I said so. That, I mean, I'm just making up various ways of limiting it. So what I would do in that case is I would say, okay, here's all my possibilities. Let me eliminate the ones that don't apply, that I'm not allowing. So I would mark these out. How many am I marking out? 1, 2, 3, 4, 5, 6. So the answer, if I said, what are the possible results are where repeated digits are not allowed, the answer would be 30. Okay, so that's kind of how those work. You can also use these tables. You could, rather than just using a dice, you could say, the other question would be, how many 2-digit numbers can you create from 1, 2, 3, 4, 5, 6? Question mark. So sometimes they give you problems that are asking about the number of possible 2-digit or 3-digit numbers that you can do, given not 9, 0 to 9, but 1 to 6, 1 to 4, whatever. And again, you can do that. You can create these 2-digit numbers, which is what I've done essentially with this same matrix, the same table of values. And so the answer for that would be 36. There are 36 2-digit numbers that you can create by using the numbers 1, 2, 3, 4, 5, and 6. Okay, so let's look at, I'm going to skip over a bunch of stuff here because we talked about it already. Let's talk about tree diagrams. So another way of coming up with the number of arrangements or combinations is to use a tree diagram. And those are used a lot for flipping coins. So what we're going to do is we're going to flip a coin, and I'm going to change it to 3 instead of 4 because I've decided to change that. So if we flip if a coin is flipped 3 times, what are the number of possible combinations of heads and tails? And the order is important. So we're not asking a question, how many combinations have two tails, we're asking what are the combinations that, whether the two tails are first or the two tails are last out of three. That's different, at least in this initial question I'm going to ask. So how do we come up with what are the different combinations? We could just start writing them down. Well, they're all heads. That would be one choice. All tails will be another choice. So that's two. And then you could just start writing numbers down. It's kind of like if you did a puzzle. Christmas time. How many people do puzzles at Christmas time? It's kind of like a family tradition. I'm not a real big puzzle person, but I like about 40 pieces. Beyond that, I lose patience. So it's good for kids, working with kids. So what do you do with puzzles? Is you look for the edges, the edge pieces and the corner pieces, so that you can at least create that. And you're looking back and forth from the picture to what your piece looks like, and you try to fit it in. You try to figure out where it's going to fit in. That's one way of doing it. You're sort of coming up with some kind of a systematic way of trying to address solving the problem. Or you could just start what kids usually do. What do kids do when they do a puzzle? They just take two pieces and they stick them together. Oh, that doesn't fit. Let me just randomly pick two pieces together and stick those together. And sometimes they fit, but they don't fit in the puzzle. The pieces fit, but they don't fit into the drawing. That's not very systematic. So we could just start randomly picking heads and tails and heads and writing them down and seeing what we get, but that's not a very efficient way of doing it. So the way you do these tree diagrams is you ask the question, how many parts are in the process? Well, I'm flipping the coin 3 times, so there's going to be 3 parts to this process. There's going to be part 1, and I'm going to flip the coin for the first time. Okay? I'm not going to write down first time. Part 2, here's you're going to flip the coin again. You're going to write it down. And the third part of the process is you're going to flip the coin again, and then you're going to get some result. Should have brought a coin in. I hate coins. I don't usually carry coins. How many people carry coins? Probably most of the women in here. No? Not anymore? Yeah. I get home, my coin goes in the bowl, and then it collects until I have enough money that I go to Walmart and get something cash for it or something like that, or put it in the Salvation Army kettle. Okay, so what you do is you list the different, so you go through the different steps and you create this tree diagram. So for part 1, if I flip a coin, what are my options? I can get a heads or I can get a tails. Now once I've flipped the coin once and I write that down, the next time I flip the coin, it doesn't matter what I got the previous step. There's no quota on heads or tails. So if I get a heads the first time, then I draw these 2 branches. And for the second flip, I can get a heads or tails in this case. And if I get a tails the first time, the second time I do it, I can get a heads or tails. So I can get heads, 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 tails. I can get tails, heads, or tails, tails. So those are my 4 possibilities if I flip 2 coins. And then you go one more step. So when I flip the coin the third time, again, the only 2 options I have are heads or tails. So for following each branch, I branch out with 2 additional choices: heads, tails, heads, tails, heads, tails, heads, tails. So what I can do now, once I've created this diagram, I could follow the branches from one side to the other, and I can get all the different combinations, all the different arrangements. So I can have heads, heads, heads. That would be one. We talked about it. That's kind of the no-brainer one, tails, tails, tails. And all the other ones in between, I just follow. I continue to go down and follow the branches. So I guess I could go this way or I could go the other way. It really doesn't matter. I usually go this way, but I'm thinking maybe it'd be easier to keep track of if I go that way. No, actually, I'm going to go the other way. So I'll do the first few, and then we'll fill out the table. So, you know, here's one possible arrangement is 3 heads, 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 heads. And then the next one, I would continue along this branch, but then when I got here, I'd go down instead of going up, so I'd have head, heads, tails. Then I've already used all of these, so I go now to the next branch further down, so I have heads, tails, heads, and then I have heads, tails, tails, and then I go down here, so I've got all of those 4, so then I'll have tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Okay, so you can see there are 8. There are 8 different arrangements. You had a funny thought, huh? I have to ask you later. Okay, so yeah, that really just reminded me. I don't think it happened in this case, but it's, you know, it's always it's kind of like the blooper videos where the guy's doing the weather forecast, you know, and he starts circling stuff, and here's this area and that area, and then all of a sudden it comes out this rude-looking or some body part, and you're like, how did that happen? So when you start laughing, I'm like, that did I do anything that maybe looks like a but anyway, so those are the 8 different ways you can flip a coin. And you know how many there are by just going to the end here. 1, 2, 3, 4, 5, 6, 7, 8. But you have to go down each branch to figure out what the arrangements are. And for you guys who've had first semester, this should look familiar because of truth tables. You know, we had the trues and falses instead of heads and tails, and you know, we would list 4 trues and 4 falses, and then 2 trues and 2 falses, 2 trues, and then we'd alternate. And then we did that because we were trying to come up with a systematic way of listing all the different ways that you can do trues and falses. And this is the same kind of thing. Now, it's kind of like filling out the table for the dice is once you've generated this, then you can ask other questions about counting. So it doesn't, this is the total number, but let's say how many tosses have at least, well, let me change it to 2 because this, I did that was with the 4 coins. If I said how many tosses of the 8 have at least 2 heads? So you can look in there and just check your inventory out. Yeah, 3. So Eli says 3. So what you're going, at least means 2, well, so this has 3 heads, but it has at least 2 heads. So we do include this one. If it just said has 2 heads, then we wouldn't include that one. We'd include this one, we'd include that one, and we'd include that one. So actually that's the question you answered. So there are 3 that have 2 heads, but there are actually 4 that have at least 2 heads. So you got to be, when they ask you these questions in the homework, you got to make sure that you pay attention to the at least kind of number. It's kind of bad, you know, when we do, what was that we did in first semester? It was I'm trying to remember what that was. It was logic tables or something like that. Okay. Anyway, so you know, the way that you can just count them from the list here. I'm just going to write them down just to show you what they are. So this one has at least 2 heads. This one has exactly 2 heads. This one has exactly 2 heads, and this one has exactly 2 heads. So the answer here is 4. If I said how many have 2 tails, then the answer there is 3. because you have, again, you could go, how many have two tails? Well, you just go through and look here. So you heads, heads, tail, that's another one, heads, tails, tails. Then you'd have heads, actually tails, heads, tails, and tails, tails, heads. So those are the three possible arrangements that have exactly two heads. Okay, so you'll get a practice at doing some of those. For if you had 4, you'd have to go one more. If you flip the coin 4 times, you'd have to include one more branch on your tree, and then you'd have 16. Now, if I had, let's say, 7, if I flipped the coin 7 times, what do you think? How many different arrangements would there be? Would you like to do a tree diagram with 7 flips? No, because 3 we would have 8. 4 we would have 16. So if you go another 3 steps, you're going to have a lot. And so what we'll find out in section 2 is there an easier way of coming up with the number based on, rather than having to list everything, can we just come up with some formula that will tell us? And it turns out there is. It's 2 to the n power. So n is the number of flips. So if we go, we'll talk about this again when we get to that chapter, but I'm just giving you previews of highlights of coming attractions. So when we had flip the coin 3 times, we had 8 possibilities. Well, 2 raised to the 3rd power, 2 times 2 times 2 is 8. And 2 raised to the 4th power is 2 times 2 times 2 times 2, which is 16. So if you flipped a coin 7 times, then it would be 2 to the 7th power, which is, anybody know what 2 to the 7th power is? 128. Yep, 128. So did you use your calculator? Did you do it in your head? Okay. So what I did, I like to, it's interesting, there's a video. There's a guy who does videos associated with electronics, and I've watched him, and he is also a high school math teacher. And he did this video of why you shouldn't be able to use calculators in math. One of them is because a lot of times when you go to higher level math, this is not higher level math, but when you go to higher level math in college, they don't let you use calculators. And so you're used to using calculators to do fractions, say. And then you don't know what to do because you're used to using a calculator. And you can't use a calculator to do fractions when they involve variables. So then you're stuck. So you need to learn to do things by hand the old way for many reasons. So throughout the semester, I will tell you about things that might help you figure out how to solve things in your head rather than having to use your calculator. So let's say 2 to the 7th power. What I would do, there's a couple of ways you can do it. One is I would break that down into something that was easier for me to do. So I know 2 to the 3rd power because that's done so often for me. That would be 8. And so 2 to the 3rd power is 8. So 2 to the 6th power would be 8 times 8. Because 6 is 2 times, the exponent is doubled. So 8 times 8 is 64, and then I have one more time I've got to multiply it, so I'd make 64 times 2, which I can do in my head, which is 128. So that's the way I would kind of break it down into things. Instead of going 2 times 2 is 4, times 2 is 8, times 2 is 16, etc. That's another way of doing it. But okay, so this is another question. We have our club again. Apparently only these 5 people can be in this club. And it says, count the different ways a president, secretary, and treasurer can be chosen if the president and treasurer must be women. So before we'll come back and answer that question, but I'm going to answer a more difficult question. I don't know if it's more difficult. It's more straightforward. So we still have the same club. how many ways can a president, secretary, and treasurer be chosen? Okay, we'll come back to this in a second. I just have another thought. So if there are 128 ways that you can flip a coin 7 times, what's the probability of getting 7 heads in a row? So there's one way out of 128. So it's 1 over 128. So that's the probability of flipping 7. So if somebody were to flip a coin 7 times and get 7 heads, and then do it again, then you'd say it's rigged, right? Just like the election was. No, until Trump won, and then it wasn't rigged. But so the latest. This is not. So the latest political news is that Jared Kushner. Does anybody know who Jared Kushner is? Jared Kushner is Donald Trump's son-in-law, and he's a real estate developer. He's probably late 30s age, worth millions, billions of dollars. He's married to Ivanka Trump, and he's been kind of one of the advisors to Trump during his. He actually is interesting. To me, he looks much more sane than Trump is. So he's actually a stabilizing force. There's a law that says you cannot appoint family members to your government. That was due to and John F. Kennedy appointed his brother Robert Kennedy to be the Attorney General, and after that happened, they've passed a law saying you can't appoint your relatives to the cabinet. It's just like if you were running a business. You can't make your son the vice president unless you own the company. But if it's a public company, you shouldn't be using family connections to fill out your jobs. So anyway, he wants to be. They want him to be the senior advisor to the president in the White House, which is not a cabinet position. So there's some debate about whether this is allowed or not. But it's kind of interesting because technically, I don't know if I'd like your son-in-law involved, but from a practical standpoint, I think actually I'd prefer him being the advisor to Trump because he doesn't listen to anybody except somebody in his family. And anybody who disagrees with him, he's probably going to toss. But you can't toss your son-in-law. So if you have a reasonable son-in-law, then that actually is strategically, or at least the safety of the United States, is a good deal. So anyway, it's interesting. It's another interesting twist to the whole presidential thing. So we can do this by using tree diagram. So there's going to be 3 parts. Part 1 is we're not flipping a coin now. We have 3 parts, and part 1 we're going to choose the president. And once we've chosen the president, then we're going to choose the treasurer. And then we're going to choose the secretary. Well, actually, because it really doesn't matter what order we do it in. We're still going to have the same number of different arrangements. So the way the tree diagram works is, how many people do we have to choose from if we choose the president first? There's going to be 5 people to choose from. Those possibilities are Alan, Bill, Kathy, David, Evelyn. Now, we do have the rule here that you can't be both president and treasurer and secretary. So once Alan has been chosen as the president, then the number of people that we can choose for treasurer has been reduced by 1. And I'm going to use letters here because it's going to get too complicated. So once Alan is chosen, when we choose a treasurer, we have Bill, we have Kathy, we have David, and we have Evelyn. Okay, so you can do the same thing for all of these others. Alan, Kathy, David, Evelyn. If we choose Bill, then these are the 4 choices that we have left. And I'm not going to do the whole thing. I'm just going to do a few legs of it so you can see how this works. And then the final step, picking a secretary. If you pick Alan and then Bill, then for the secretary you can choose Kathy, David, or Evelyn. If you choose, let's say you choose Evelyn as your treasurer and you choose Alan as your president, then you're going to be able to choose Bill, the ones that haven't been used yet, Bill, Kathy, and David. And if I continue those out, then I'm going to get 3 from this branch. I'm going to get 3 here, 3 here, 3 there, all the way through that. And if I did that, it would turn out there are 60 different ways. There'd be 60. That's why I'm not going to spend the time doing it. But you can see what I would do is I would go Bill and David and Evelyn, and this branch would be that way. So you can see it gets pretty complicated if you have to use tree diagrams all the time. Now, in the case of the first question, so the answer here, it turns out to be 60, and I'll explain why there's 60 different ones in a second. But let's go back to the original question, because this tree diagram is a lot simpler. That's probably why they put it here. So you'd have the same situation. You have part 1, you choose a president. Part 2 would be to choose the secretary. And part 3 would be to choose the treasurer. So when we choose the president, what does it say here? It says, count the different ways a president, secretary, and treasurer can be chosen if the president and the treasurer are a woman. So we don't have 5 choices here as president. We only have 2 choices. We have Kathy, and we have Evelyn. Now, when we go to pick secretary, Kathy can't be chosen as secretary because she's already been chosen just like before. And the same way is true. So, so what we'd have is Alan, Bill, David, and you might be tempted to put Evelyn here. But why can't I put Evelyn? Yeah, it doesn't say I can't it doesn't say I can't have a woman treasurer. But there's some other thing. If I choose Evelyn, who's left over to be secretary? Actually, who's left over to be treasurer? So if I choose Evelyn as secretary, then there's nobody left over to choose as treasurer, which has to be a woman. So that's why I can't include Evelyn, because she's needed for the next position. So I'm going to erase Evelyn because that doesn't work. So once I've chosen Kathy and Alan, the only person left over here is Evelyn, and it's the same case for every situation. So this is much more doable. David. And then we have Kathy. And so if I list all these out, I can get there's 6. There's 6 different ways of choosing a president, a secretary, and treasurer if the president and the treasurer must be women. And you can, the choices are Kathy, Alan, Evelyn, Kathy, Bill, Evelyn, Kathy, David, Evelyn, Alan, Kathy, Evelyn, Bill, Kathy, and Evelyn, David, Kathy. So the answer is 6. I'm just counting. I've listed everybody. I've counted them. I give the answer. Okay, I'm going to delete that page. Well, I'll leave that up there. I'll come back to that in a second, but let me. No. Here's your homework assignment. So I'm going to go ahead and assign section 1 today, which means you should turn it in next Tuesday. Excuse me. So anybody do anything fun over Christmas break? You doing good? Yeah, that's true. Yeah, I left Friday after exams and drove to New York because it was supposed to snow Saturday. So I was originally going to go Saturday. Spent 2 weeks with my older daughter and the twins and Zach, and we stopped on the way back into Alexandria to visit Heather and Kevin and Xander. So we were gone all of Christmas except for 1.5 days. So that was interesting, not being home for Christmas. It was fun. Okay, so we're going to do one more problem, which is on the left-hand side there. How many 3-digit numbers have the sum of their digits to be 21? So this is an example of where you would use a tree diagram. First thing is to understand what the problem is asking. Does anybody know a 3-digit number, just one example of a 3-digit number whose sum of the digits is 22? You got to add the individual ones. So 220 would be 4. 2 plus 2 plus 0. Yeah. So like 333 would be 3 plus 3 plus 3. So you'd have to have 9 would be a good first choice. 9 plus 4. Yeah. 9 plus 9 plus 4, because you'd have 9 plus 9 is 18 plus 4 is 22. So that's one example. So let's just, so 9 being the first 2 digits probably is a good, so 9, so our first digit could be 9, it could be 8. I'm not sure exactly how small I can make the first digit and make the thing work out. And you kind of have to go along. So so for 9 being first digit, the second digit being 9, the third digit would be 4. 9 plus 9 plus, that's one you just gave me. Now with 9 being the first digit, if I decreased this digit to 8, what would I have to do to the third digit? Yeah, increase it by 1. So I can use that pattern to kind of figure out how to do this. So as I keep decreasing this one, I have to keep increasing that one, and I can do that until I get too big. I only can go so big. So after that, I'm done. I mean, I'm not done completely, but I'm done with 9 being the first digit. So I've got 9 plus 9 is 18 plus 4 is 22. 9 plus 8 is 17, plus 5 is 22, and I decrease this by 1 until that gets as big as I can make it. So there are six 3-digit numbers that start with 9 that add up. So you could do the same thing for 8. So let me just make a little more space on this thing. And we really can, let's see, so if I say 8, and then I have 8, 9, then this would be 5. So it's like 9, 8, 5. Instead, you have 8, 9. You just switch these two. So that's, and again, if I decrease this by 1, I'd have to increase this by 1. And so I just follow that pattern until my last digit is a 9. So there are 6 of these. How many of those are there? There are 5. So with the first digit being 8, there are 5 different possibilities that add up to 22. How many do you think there are for 7? If there's 6 for 9 and there's 5 for 8, there probably is 4 for 7 and 3 for 6. And because what's driving this, what's limiting the number is this. And so when I make this one smaller, it's going to eliminate one of them. So I'm not going to write every one of them. I'm going to do what kind of reasoning is where you make multiple observations and then you come up with some general conclusion. Do you remember? What's that? Well, you had a 50% chance. It's inductive reasoning. So from first semester, inductive is where you observe stuff and then you kind of conclude something. So what I observed here was that every time I reduce this number by 1, my number of digits is reduced. The number of numbers is reduced by 1. So if the first digit is 7, there's going to be 4 choices. If the first digit is 6, there's going to be 3 choices. If the first digit is 5, there's going to be 2 choices. And if the first digit is 4, there's going to be 1 choice, which is going to be 499. So the total number, if I add all these up, are going to be, I'm going to add all these up. 6 plus 5 is 11, plus 4 is 15, plus 3 is 18, plus 2 is 20, plus 1 is 21. So the answer to this problem is 21. There are 21 3-digit numbers whose digits add up to 21, or 22. 22. There are 21 that add up to 22. So again, it was something it didn't just come like that to us. We had to figure out some way of, first we had to understand the problem, which you guys did. You came up with one example, and once we had the one example, then we could kind of, and then we came up with a pattern that allowed us to make some inductive conclusions so that I didn't have to list all of them. I mean, there's no reason why I couldn't have listed all of them, except I would have run over the time period if I had done that. So, okay. So if anybody needs a book, which you guys do, just hang around for a second and I'll take you over to my office, then you'll know where my office is.